Okay, guys, in this video lesson, we're going to take this idea of universal law of gravitation, okay, and that force that gravity provides us, and then talk about what is G then, okay? So the idea here is, how do we get G? What is G? How does that kind of stuff work, okay? So first thing we want to talk about is a quick reminder that G is the acceleration that gravity causes, okay? Early in the year, a lot of times, we kind of let it slide that people talk about, oh, well, that's G. Well, G is not a force. Little g is an acceleration, right? It's the same thing as a in our equations. It's the acceleration. Okay? Now, another way to look at little g is called the gravitational field strength. Okay? So if you have an object and it is within the gravitational field of another object, there is a certain amount of strength of attraction that happens there that causes this acceleration. Okay? We tag that as measured in newtons per kilogram. Okay, it's still an acceleration. It's the acceleration you feel because of this field strength caused by the bigger or the larger object. Okay, so it's still a result of this gravitational pull that we have between two objects. We just get another term. Okay, so little g can also be called the gravitational field strength. Okay, what it comes down to is it's basically, it relates back to your mass now, because it's the newtons of force per kilogram of an object that you have. Okay, so essentially it comes down to is how many newtons does each kilogram get pulled by. All right, so if I'm 100 kilograms, that tells me, well, I want to have a certain number of newtons times 100 is going to what I want to feel for the gravitational pull on me, which would be my weight ultimately. Okay, but just another way of looking at little g. Okay, now, one thing we need to realize is that even though up until this point we've been talking about G, or the 9.81, as being something that is always this 9.81, it's always 9.81, it's always 9.81, that is somewhat true. Okay, it is true that G is 9.81 at the average distance from our planet, or basically at sea level. Okay, so if we take a look, if our Earth was a perfect sphere, and we looked at sea level, 9.81 would be the value of G. Okay. However, if we get further away to the tops of mountaintops, it could be even lower, 7.4. If we get even further away, it could even be lower, 4.9 newtons per kilogram. Okay. If you get further away, down to 2.5 to 0.98. So as an object moves further and further away from sea level, the G value, or the field strength that is felt there, goes down. Okay, the acceleration goes down. Okay, if we were to get closer, it would go up. Okay, in terms of what we have there between those two different things. All right, so we use 9.81 because that's a pretty good average for us, but it isn't necessarily the exact same at all points. Okay, now why is it 9.81? Okay, so why this number? We can do the math on it actually and solve for this. Well, to do that, we need to have a couple equations that we've been using. The first equation, the force of gravity, is mass times acceleration due to gravity. Okay, we've been using this a lot. Our new equation, universal law of gravitation, the force of gravity, is also equal to the gravitational constant, mass of your object times the mass of the Earth divided by the radius squared. Okay, so these are two equations we have. So now what we're going to do is we're going to set this equal to this. So now we can say that the mass of the object equals, times acceleration, equals the universal law of gravitation, mass of object, mass of Earth, divided by radius squared. But if you notice, the mass of the object is here, the mass of the object is here also. So we have it in two different places. Okay? So in reality, we talk a lot about how the mass doesn't matter. Okay, we talked about free fall. Everything falls at the same rate. It's the same acceleration. It doesn't matter if you're a 20-pound bowling ball or a 1-pound volleyball. Ignoring air resistance, they all fell at the same rate. Okay, we saw it. We experimented with it. We know it's true. Here's why. Okay, the reason why is if Newton's second law holds true, that mass is times acceleration, and we know that universal law holds true, mass is in both sides of this equation, so we can cancel it out. Which means the acceleration that an object feels, okay, or the field force that is pulled on it, is actually equal to the universal law of gravitation's constant times the mass of the object, in this case Earth, divided by the distance you are from each other. Okay? So let's work it out then, okay? We know the radius of the Earth is 6.37 times 10 to the 6 meters. We know the universal the universal gravitation constant. We have the mass of the Earth. So we have all the variables that we need. Okay, let's plug our numbers in. So 6.67 times 10 to the negative 11th, 5.97 times 10 to the 24th kilograms, the radius squared, and if you solve for little g, okay, at sea level, we get 9.81 newtons per kilogram. Okay, so that's where the 9.81 comes from. Okay, it's the acceleration that any object is going to feel because the mass does not matter of the object. Right? That field strength that it feels solely comes from the mass of the object pulling on it and how far away it is from that object. But the Earth is not a perfect sphere, which means that value of 9.81 doesn't hold true in all places on our planet. So let's calculate the maximum value of g and the minimum value of g that we can find. Okay? So first of all, let's talk about the minimum. So how far away can we get and still be on our planet? Okay? You might think that might be Everest or even Kilimanjaro, okay? Some of our highest peaks out there. However, because the Earth is not a perfect sphere, okay, it's actually wider at the equator and it's narrower at the poles. Okay? Any mountain region that is at the equator has an advantage because our planet is actually not a perfect sphere. Okay? In fact, it gets shorter and fatter as time goes on because of its own inertia. As our planet spins on its axis, its inertia is constantly trying to pull it apart. Okay? Its own gravity and the strength of the planet holds it together, but eventually it's going to get shorter and flatter and fatter and fatter. Okay? That's how it's going to work. What that means is, as long as we find that mountain range that has the values the highest from the center of the planet, that would be Chimborazo, I think it's pronounced, mountain that has a radius of our Earth of 6.384 times 10 to the 6 meters. Now, the closest we can get to our center of our planet is actually at the bottom of the Arctic Ocean because we're at one of the poles and we go down in terms of below the water surface to get down as low as possible there. That would be 6.353 times 10 to the 6 meters. Okay? If we now plug those numbers in for the math, exact same math as we did before, okay, just a new radius. We still use the universal constant for gravitation. We still have the mass of the Earth. We got our new radius in squared. Even though it's a very small change, g changes to 9.77 newtons per kilogram. Okay, so not a huge change. In fact, if we round it off to two significant figures, it's still 9.8. Okay, if we go to the maximum radius here, we get 6.353 times 10 to the 6 squared, and we get 9.871. Okay, so really, if you take a look at these, between these two things, between those, we're still at 9.8, 9.9, no matter what we have here for our value of g. Okay, so the 9.8 number or 9.81 number is a really good approximation for the acceleration of gravity or the field strength that we have for any object on our planet. Okay, so that's how we do it. All right, guys, that finishes this video lesson. In our next lesson, we will talk about Newton a little bit more and his thought experiment with the cannon and get into orbital and escape velocities. Thank you.